I didn't review the video to see exactly how I ended last time, but I know that we had gone through the quantum mechanical model. We had gone through and looked at each one of the different orbitals, and I'm not going to show them again today, but this general graphic allows us to look at them and to remember them. Hopefully you can see within this, first of all, that there's a nucleus, right? The nucleus here is portrayed by these red and blue balls in the middle. They are protons and neutrons, that's what it's trying to show. And that around those neutrons are the electrons. Around those neutrons and protons, around the nucleus, are the electrons. The electrons aren't in the shapes like we looked at historically. We had the Dalton model, everything is one big chunk. We had plum pudding, we had Thomson. Thomson went to the nuclear, meaning that there was a nucleus with electrons on the outside. Went to this kind of, then we went to the Bohr, and we said that with the Bohr, electrons were on the outside and they were kind of in orbits, and not only were they in orbits, but they were in orbits of increasing energy level, so there was kind of presented as rings, like rings in a tree, lower energy level, higher, 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 like that. And then we said all that's useful and all that's necessary, but none of that is the way we currently understand the atom. It's ways of understanding it, but there's a way which even more accurately reflects the current understanding of what the atom looks like. And would even offer that ultimately this might be wrong too. So it's up to you all to move us to the next level of modeling, right? It's for future generations to look at it and say, wait a minute. And they may, and that's one of the errors of every generation, is think they've got it all figured out, and everybody before them was stupid, and everybody else after them will appreciate them. The fact of the matter is, in the future, they'll look back at you and how stupid you are too, because they believe they've advanced so much. But guess what? The future will look back at them as well and go, how ancient were they in their understanding? So it's in this constant chain of more accurately modeling reality. And for right now, this is what we have as the best model, the quantum mechanical model. But it's not like Bohr's model. It's not two-dimensional with electrons orbiting in rings, racetracks, but rather it's a three-dimensional shape, and it shows not where the electrons will be, but where the electrons will probably be. And they fill not in all spheres, but we see right there the p orbitals. They look like dumbbells. We mentioned s's, p's, d's, and f's. And the only two you really have to be able to draw, to conceptualize and put down on paper, are the s's and the p's. The s orbitals are spheres, they're balls. And that's what we see here. This is a 1s orbital and the 2s orbital right there. Concentric spheres. The nucleus is always in the middle. For every orbital, the nucleus is always dead center middle. Okay? And from that, for the s orbitals, they build as concentric spheres, or think of them as I mentioned yesterday, the Russian dolls, okay? Whatever, Nunchunka dolls or something like that. But anyway, there's a larger sphere. It's a larger energy level. As you look inside, there's a smaller sphere that's a smaller energy level, smaller and smaller until you get all the way down to the 1s orbital, and then inside the 1s orbital in the very center is the nucleus. But the s orbitals, that's not the only shape, that's not the only orbitals that we have. We also have the p orbitals, which look like the dumbbells. The first energy level only has the s orbital. The second energy level has the s orbital and the p orbitals. The third energy level has the s orbitals, the p orbitals, and the d orbitals. The fourth energy level has the s orbitals, the p orbitals, the d orbitals, and the f orbitals. S's are spheres, simple circular spheres, S. P orbitals are the dumbbells. D's and F's, know they exist, don't worry about what they look like. We need computer programs to draw them, they get kind of funky. All right. We mentioned that these orbitals, as they fill, they need to account for every single electron that's in the atom. And they fill in a particular order. Now what's shown up here, if you look underneath the arrows, you see the 1s2, 2s2, 2p6. For those of you that weren't here, the first number indicates the energy level. If you think of the Bohr model, the innermost circle would be the first energy level, the second energy level, the third energy level, the fourth energy level. So just think of it that way. And we mentioned yesterday too on the periodic table that that energy level corresponds to the row across where the element is at. Or in this case, the electrons fill according to those rows. Those rows indicate the energy level, and here the first energy level, the second energy level, the third energy level, and so on. Within each energy level, there's an option of orbitals, but they don't simply fill from left to right, top to bottom. They fill in a paradigm which can be shown in two different ways. One is according to this slant diagram, meaning that we fill according to the slant. So the first position we're going to fill is the 1s1. The second position is the 1s2. The third position is going to be the 2s1, and then the 2s2. And then the 2p1, the 2p2, a 2p3, a 2p4, a 2p5, a 2p6, and then a 3s1, and then a 3s2. See, these just show the maximum number. You can have a 2p3, 4, 5, 6. You can't have a 2p7. The 2p7 would actually fill the 3s1 position, and they fill in that order. We also mentioned yesterday that that corresponds to the periodic table. Okay. And the periodic table has a lot of information in it. Some of it we've only just touched upon. We mentioned how that technically hydrogen, over here in the column 1A, first row position, it's on the metals side of the chart, but if we're considering metals, it should technically be over here. So when we're doing metal, non-metal based upon the jagged line, hydrogen is misplaced and it should be over by helium. When we're doing orbitals, helium is misplaced and it should be over here next to hydrogen. See the compromise? And what's happening here is on the periodic table, we can tell what orbitals are filled based upon where the element is on the periodic table. The 1s, or the 1 first energy level, is the first row. The second energy level, second row, and so on. What orbitals are being filled fill in order across from left to right. The s orbitals, the p orbitals, and then when we get down here to the fourth energy level, after the 4s1, the 4s2, then we start filling the d's. But remember, when we fill the d's, we need to decrease the energy level by 1. So a 4s1, 4s2, this now becomes 3d1, 3d2, 3d3, and so on. At the end of the d's, we go back to the original energy level 4, 4p1 through 4p6. And when we find any element on the periodic table, we can build its entire configuration simply by starting at the top and writing it down in order until we get to that element. And we stop at its valence shell, its outermost shell, with the number of electrons that are remaining that need to be placed. Now, we haven't actually been able to do much of this other than hydrogen, helium, lithium, and beryllium, right? So we're going to do a few of the examples in here and kind of nail this concept into your thinking. How are we going to write down the complete electron configuration of any element? Where do those electrons reside? What orbitals are they in? In what energy levels are they in? Remember that every orbital can contain 2 electrons, which is why the 1s, or any s level, only has 2 electrons in it, which is why the s group only has 2 columns. So I may not know the full configuration, but I can tell you, for example, as I look over here at magnesium, that its outermost electron is in the s2 position. I can tell you here that it's the 3s2 position. Why? Where it's located, the block it's in, and the level it's on indicate its outermost electron configuration. Getting it, not getting it, fuzzy, simple, where are we at on this? Like, I got it, I don't have a clue what you're talking about. Where are we at? Is it starting to make a little bit of sense? Okay, good. Getting some, yeah, okay. And I think once you see it, once we do a few more other than the very simplest ones, you'll go, oh, okay, that makes sense. So let's do that. We mentioned yesterday about the carbon atom. Write the electron configuration of a carbon atom. The very first thing we need to do to figure out where these electrons reside is to figure out how many of them do we have to place. Now it's a carbon atom. So what do we know? If it's a carbon atom, we know, based upon the periodic table, its atomic mass and its atomic number. We're concerned about the number of electrons we need to place. We can determine how many electrons we need to place based upon the atomic number, because the atomic number equals the number of protons, and it also equals the number of electrons, correct? So carbon is an atomic number of 6, which tells me that I have to place 6 electrons. Think of it this way. You're actually trying to find a home for these 6 stray puppies, right? And you've got one family that'll take 2, and one family that could take up to 6, right? So the S families can take 2, the P families can take 6. The D families, man, they must own a kennel on the side because they can take 10. And the Fs, man, they own a farm. They can take 14. Okay, so you're trying to place the puppies. Here in carbon, you've got 6 electrons. You're trying to find a home for 6 electrons. Where are you going to put them? Pardon? Well, we've got to start by filling from bottom up according to the slant diagram or the periodic table, whichever way it looks. So let's first of all look to the periodic table. I have to place 6 of them. Now, if I look at the periodic table, I've got the column, the first 2, 1s2, right? I can place the 1s2, that's 2. What's the next shell that, or next orbital that I begin to fill? 2s2. And I can place 2. I've now placed 4. How many do I have to place? 6. What's the next orbital I start to fill? The 2p. How many do I have to place? 2. So I have 2 in the 1s, 2 in the 2s, and 2 in the 2p. And that's why the electron configuration is a 1s2, 2s2, 2p2. The 2p orbitals can hold up to 6 electrons. Remember, there's 3 p orbitals. They all go in cardinal directions, the x, y, and z axis. So the 3 of them totally can hold 6. I only need them to take 2. And so that's the electron configuration for carbon. 1s2, 2s2, 2p2. Now if I go through and add up all my numbers, all my superscripts, 2, 4, 6. There's my 6. Found a home for all of them. And so when later on when we draw the carbon atom, we're gonna need to know that those numbers, because it's the outermost electrons, the valence electrons, that determine the chemistry of the atom. And we're going to need to know that number right there for future lessons. But before we can figure out what that number is, we need to fill them all up to that point to make sure we've got it right. So carbon is a 1s2, 2s2, 2p2. Another one. This is all example 3, 4 in your book, which is on page 121, 122. That was, the last one was on 121. This is 122. Write the electron configuration of a chlorine atom. First thing I'm going to do is what? Find chlorine on the periodic table. Because when I find chlorine on the periodic table, I can look at its atomic number. And when I have the atomic number, I have the number of protons and the number of electrons. What is the number for chlorine? 17? Well, yep, chlorine's right over here next to argon. It's 17. So the atomic number of 17 means 17 protons, 17 electrons. I need to place 17 electrons. So if you have your slant diagram in front of you, you can just go back to that and start counting them up, right? So we have a 1s2, 2s2, 2p6, that gives us 10, 3s2, that gives us 12. We need to place 17, so we need to place 5 more. And what is the next orbital to be filled? The 3p, right? 1s2, 2s2, 2p6, 3s2, 3p5. 3p5, because we don't need all 6 positions, we only need 5 of them. And they add up to 2, 4, 10, 12, 17. That's my configuration. So adding up the superscripts lets you know if your count is right. You need to make sure you fill the energy level and the orbital in the correct sequence. That correct sequence is either from your slant diagram or looking at the periodic table. Do you see for chlorine, I'm coming over here to the periodic table, that I've got to fill the 1s, so 1s1, 1s2, 2s2, 2p6, 3s2, 3p, 1, 2, 3, 4, 5. And that's the same as the configuration I've written on the board. So again, This is the 1s, the 2s, the 2p, the 3s. Those are all full completely. Now I'm over here to the 3p. 1, 2, 3, 4, 5, and that's my superscript. 3p5. Ready for the next one? Make sense? A little bit of a bobble, yes or no, please. Just a little bit. Okay, moving on. 3.4c. What is the electron configuration of a silver atom? Okay, silver. It's pretty intimidating. It's all the way down here. 47. That's hard. The number's so big. I can do 6 or 8, but I can't do 47. Nonsense. Right? If you look at your slant diagram, or frankly, I told you slant diagram is the only way I learned it. But the periodic table is so much easier. It's so much easier. So if you're going to default to one or the other, now the plan for this class is for that periodic table to be there for the whole year. Okay? We may have to put up a smartboard over there and move the periodic table, but you will always have access to a periodic table for your exams. So learn how to do this by the periodic table. It's so much quicker, so much straightforward. Let's do silver together from the periodic table. I know this is off camera, but hopefully you can still follow it at home. Here we go. We're going to find silver. Number 47. It's right here. In what section is this? What orbitals are we filling here? D's. Okay. Let's fill the orbitals. So we're coming up with the electron configuration of silver, 47. We're going to look, first of all, start from the top left and work all the way down. We have the 1s, 2. 2s, 2. 2p, 6. 3s, 2. 3p, 6. 4s, 2. 4s2, this becomes what? 3d, 10. Now we're past the d's, we're back to the p's. We go back to the correct energy level. Now we're back at 4p6. 5s2. Now we move into the d's, so we have to reduce the energy level by 1. So it's 4d, 1, 2, 3, 4, 5, 6, 7, 8, 9. There's the electron configuration. And ultimately, the chemistry of silver is going to be dictated by, or we're going to see that this number 9 here is going to be a very important number for us. So we need to be able to figure out what that is. We can figure out what that is. If I don't need to know anything else about the configuration, let's go back over to chlorine. If I come over here to chlorine, because it's in a column 7, it's a column 7 element, okay? I'm going to know, for example, that there's 7 electrons in its valence shell. I'm also going to know, because it's over here, that the last electron that I place in its configuration is a 3p5 electron. And so if I had the slant diagram, I would count up to 3p5 and stop. So you kind of use both methods at the same time if you need to. But again, hopefully you see that graphically on the periodic table, it's a much easier, much sweeter way of doing this thing. Any questions on silver and how we came up with 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d9? And you hopefully see that this is pretty simple to get, right? But you know what? That string of numbers and superscripts and everything, yesterday, for some of you, you would have seen that and go, oh, I can't do chemistry. Look at how hard it is. Come on. It's a piece of cake. So let's go ahead and push it a little bit more. On your own, write the electron configuration for silicon. Go ahead, put it in your notes. Electron configuration for silicon. Now, to help you out just a bit, where is silicon? Atomic number 14. As a hint to the whole class, what is the last electron that gets placed in the electron configuration diagram? What energy level? It's, what row is it in? It's in the 3rd row, right? So the coefficient in front is going to be a 3, third energy level. What block is it in? P. What position is it in? 2. So 3p2 should be your last orbitals that are full. Your 3p2. Anybody need more time? I mean, really, okay, take a few more moments. Especially if you were absent yesterday, I understand. But hopefully you're seeing that this is like, got it. This is just okay. 2, 2, 6, 2, 6, 2, 10, 6, 2, 10, 6, 2, 10, 6, 2, 10, 14. We'll get to that eventually. 14 jumps in there because, see, 14 is between 57 here, between 56 and boom, then you go down from the D block to the F block. But frankly, we'll spend such little time there, don't worry about it. Right now, if you get the S's, the P's, and the D's in the paradigm, you're good. Okay, should look something like this. 1s2, 2s2, 2p6, 3s2, 3p2. 2, 2, 6, 2, 2. We haven't hit the fourth energy level yet, so we haven't had to even touch the D's, so we can't make the mistake of forgetting to remove one energy level from the D's. But again, hopefully you're seeing that this coefficient here indicates the energy level, which on the periodic table is the rho. The second is the orbitals that are being filled, S block, P block, D block, and F block. And then the numbers are how many of those positions are being taken up for each one of those orbitals, so that the superscripts all add up to be the atomic number of the element. On your own 3-9, do the same thing for selenium. Selenium's over here, number 34. As a class, the last electron to be placed will be where? What energy level? 4, what orbital? P orbitals, which position? 1, 2, 3, 4. 4p4 should be your last electrons placed. So, just look it up there with me. Do you see the 1s2 is full? The 2s2 is full. The 2p6 is full. The 3s2 is full. The 3p6 is full. The 4s2 is full. The 3d10 is full. And the 4p, 1, 2, 3, 4 is your last positions. Again, these are in your book, so if you don't get the numbers, you can check back the answers on your own. But then we go to silver again, right? Didn't we just do silver? We did silver already. So they gave you an on your own, which is actually one of the example problems. So they just repeated it. You could look at either place. The same thing, though, and we know we're right. Let's go over here to silver again. Silver is right here. The last electrons placed. Silver is in which row? It's in the 5th row, so it's in the 5th row, but it's also in the D block, right? So because it's in the D block, our highest energy level that we're going to be, or the last electrons we're going to place, are in the 4th energy level because they're in the D of the 5th row. So you can see where the 4D comes from. And it's the 9th position within the D block. 1, 2, 3, 4, 5, 6, 7, 8, 9, which is why 4D9 is the last position on the electron configuration. Now, the last bit of instruction for the module that we're going to cover in here recognizes that, you know what, for a lot of these elements, didn't you realize that you're repeating the same information over and over and over again? Mr. Baker, how many times am I have to write 1s2, 2s2, 2p6, 3s2, 3p6, blah, 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 blah? You know, like, there's got to be a simpler way. Dude, there's a simpler way. We're going to make it simple. Now, The thing you've got to understand is when you look at the questions, it'll say write the electron configuration. It may say write the full electron configuration. This is what you need to write. But there are times when it's going to say give the abbreviated electron configuration for the element. So you need to know how to do the longhand, but now I'm going to show you the shortcut. Because yes, writing 1s2, 2s2, 2p6, 3s2, 3p6, 4s2 gets redundant over time. So what we need to do is look at our periodic table, and we're going to look all the way to the column 8a, all the way to the right, and look at those things which we refer to as the noble gases. Now the noble gases, and we'll learn this later on, have particular properties in that, frankly, they don't like to play with others. Remember we said about personifying elements, and they don't really personify, but they kind of have character traits, and we say, like, for example, the electrons want to get to the lowest energy level, but there's no emotional effect going on there with the electron. It's not a thinking process. It's natural, okay? Here we're going to say the noble gases don't like to play with others. So you know what? They're not thinking about, oh, I want to stay away from people. I want to stay away from other gases. It's just part of the nature of the noble gases is that, and we're going to learn this later, remember we said the chemistry depends upon their valence electrons, their outer shell electrons? Well, guess what? We're going to learn that the noble gases, they already have all they want. They don't want to give up anything, and they don't want to get anything. So the only time they ever react is when they're forced to in a process, a chemical reaction, because of energy or something like that. Naturally speaking, they're not reacting with anyone. That's why they're called, in the noble gases, they're non-reactive gases. You usually use them with other things because they're not going to react with anything. They fill a space and they're identifiable, but they tend not to react with anything. Which is why they make a nice solid basis for what we're going to do here, writing an abbreviated electron configuration. So the noble gases here, helium, neon, argon, krypton, xenon, and radon. Right down that column there. We're going to use their characteristics as kind of like a benchmark, a base to build up from. Here's what we're going to do. First of all, when you're building the abbreviated configuration, what I want you to do is go to the periodic table and locate the element. Find it on the periodic table. You've been doing that already, right? Going there just to find the number. Once you find its number, you can count up using the slant diagram, or you can put your finger on it and count and build the different orbitals, 1s2, 2s2, 2p6, and build it up until you get to the place where your finger's at, and then stop. When you do that process, you've always been starting at hydrogen, right? 1s2, okay, then looking down to lithium, that's 2s2, 2p6. So every time you've done this, graphically, you started up at the top left corner and built all the way down. What we're going to do, though, is we're going to stop starting from the beginning. And we're going to start at the preceding noble gas. So you locate the elements you need to build the abbreviated configuration for. Then you locate the preceding noble gas. How do you do that? You locate your element wherever it is on the periodic table. Let's go back to silver again. We've used that a couple times. So silver is at 47. I need to locate the preceding noble gas. All I need to do is pop up one row and go all the way to the right. From silver, the preceding noble gas is krypton. From silicon, the preceding noble gas, I go up a row and all the way to the right, it's neon. As a matter of fact, for this entire row here, from bromine, I'm on the 4th energy level now, from bromine all the way across to potassium, the preceding noble gas for that whole row is argon. So you find the element you're trying to build the abbreviated configuration for, you locate it on the periodic table, you move up one row and go all the way to the right and identify the preceding noble gas. Then you just build up the electron configuration from there. And the way you're going to show that this is the abbreviated form is you're going to put the noble gas, the chemical symbol, in brackets. So for example, if I've set up here an example would be putting xenon in brackets. If I'm building an abbreviated electron configuration for something and I'm starting it with a bracketed xenon, that means if this is my noble gas, number 54 xenon, that means that what I'm building up from that exists somewhere in the row below it, excluding radon, because radon would be its own noble gas. Okay? So anything in this row here is going to start with xenon. Anything here on this row is going to start with krypton. Anything in this row here is going to start with argon. And then I'm just going to build it from that point. I'm going to look at the graph. Since I'm all the way at the right-hand side, I write the noble gas, and then I jump to the next row down and all the way to the left, and I start building from the next energy level, S. And just go from there. So let's try a couple. That last one here, and build it up from there, just so you have your notes. Locate it, locate the preceding noble, write the preceding noble in brackets, and then build up your configuration starting at that point. Example 3a, write the abbreviated electron configuration for strontium. Strontium is a column 2a element. It's in the 5th energy level. It's over here, number 38. Okay? Let's do the process. Strontium 38, or excuse me, atomic number 38. I need to go and locate the preceding noble gas. What is that preceding noble gas? Go ahead and say it. Krypton. Superman, right? Kryptonite. Krypton. Same thing. Well, doesn't have the same effect, but you know what I mean. Anyway, so from strontium, we go up a row and all the way to the right, we get krypton. So my abbreviated electron configuration is going to start with capital K, lowercase r in brackets. And where do I go from there? Well, I move on. So from krypton, and I'm working my way to Sr, strontium. What do I add to krypton? 5s2. So my entire configuration would look like this. You just said the last placement would be a 5s2, right? If I did the slant diagram, it would look like this. When I use the abbreviated, all of this, from the 1s2 to the 4p6, that's all the same as the electron configuration of krypton. So I replace all of that with krypton. And then just go from there. Krypton, the noble gas, has from a 1s2 all the way up through a 4p6 electron configuration. If I replace that with krypton, then all I have to do is show what I needed to build up from there, my 5s2. And I'm done. Selenium. Not selenium gomesdium, but right? Selenium. What is the atomic number of selenium? Have you found it?
34.
34. Good. So it's a column 6a element on the 4th energy level. Take just a minute, put that down in your notes. Okay. So looking at selenium, atomic number 34, what is the preceding noble gas? Argon, correct. So we're in the 4th row, we move up to the 3rd row, all the way to the right, it's argon. So my configuration is going to start with argon. What is the last placement for my energy, or excuse me, my last electron placement going to be for selenium? Do you see that it's going to be a 4, okay, energy level 4, orbital p, location 4p4, okay? So I've got argon. What do I do when I build up for there? Here's 4p4. That's what the complete electron configuration looks like. Now if I look up to argon before that, then I build from argon, what's my next placement going to be? After the 3p6 of argon, I have the 4s2. Then I go to the D level, where scandium is. I've got to reduce the energy level by 1, which makes it a 3. And then I fill all 10 positions, which is where I get the 3d10 from. Then I go back to the 4th energy level on the p block, and I fill 4 of those positions. Argon is all of this, from 1s2 up through 3p6. So I can replace all of that with argon and then build from there, the 4s2, the 3d10, and the 4p4. See, because argon has 18, right? Its atomic number is 18. Notice here, 2, 4, 10, 11, 12, 18. So I abbreviate it by replacing the configuration of argon with the symbol argon because it is a noble gas, and then I build up from that point until I'm done. On your own 311, what is the abbreviated electron configuration for bromine? Not bromide, because there'd be one less, right? Or that would be an ion. We haven't really gotten there yet, but don't worry about it. So bromine, the atom bromine, the neutral atom, meaning it's got the same number of protons and electrons. What might you notice that's familiar from the last problem? Same thing with one more electron, right? Let's pretend we didn't know that. We're going to start with what element? Argon, right? And we're going to build up from there. So we're going to have argon, and then place in brackets. Let's do it together. After argon, we're going to fill the what? What energy level? 4. Orbital s, both of them, right? Then we go to the 3d, and we need all of them, don't we? So 3d10. Then we go back to the 4th energy level p, and we fill how many of them? 4p5. Okay. Yes, ma'am.
If this is on our test, do you want us to write it all out like that on the board, or just do like the bottom one?
You don't need to do this step. You will be asked for either the full, which will be this. Put it this way, unless you're asked for the abbreviated, this is what you're expected to give. When you're asked for the abbreviated, you can give this. That center step there, I'm just doing to show you where that comes from. That argon is this configuration. So you're accounting for all of those electrons by putting argon in the bracket. Configuration of indium. Atomic number is 49. Okay? So let's build it up from there. What are we going to put in brackets? Krypton, right? Go up a row, or go up one row and all the way to the right. The preceding noble gas is krypton. Put that in brackets. Then let's build it up from there. After krypton, we have 5s. We need both of them. That's 5s2. Then we go to the d level. What energy level does that become? 4, because it's in row 5, but we have to subtract 1 when we get to the d level. So it's 4d. We need all of them. 4d10. Then we go back to the p. We go back to the correct energy level. 5p1. And then when we start talking about valence shell electrons and reactions and things like that, you're going to need to be able to go back to this and say, how many electrons are in the highest energy level, or the valence shell? And for our purposes there, we're going to look to the highest number that we have. What's the highest energy level in this? What's the highest energy level? What's the highest energy level? Another way of saying that is, what is the largest coefficient you see here? 5. You see a 4, but you see a 5. Which is bigger, 4 or 5? Okay, good. We're ready for chemistry. 5 is bigger than 4. So how many electrons are in the 5th energy level? 1, 2, 3. The chemistry of this element is going to be determined by the fact that it has 3 electrons in its highest energy level. Yes?
Did you just do that because both of the
Mm-hmm. Yep. I added up how many do I have that are in the 5. And hopefully pick up the pattern here, since we reduce the number for the D's and we're going to reduce the number for the F's, that basically your S and P orbitals are going to determine the chemistry of every element. Oh, and here's the other trick. A little bit ahead, but we're going to get there soon. The number of electrons in the valence shell, the highest energy level, is going to be the same as the column that it's in. This is all an S1. There's 1 electron in its highest energy level. Over here, guess how many there are in the highest energy level? 2. Over here, how many? 3. You got 2 for the S, right? No, it's column 1A, not the top, the bottom. Because we're going to learn also the octet rule, meaning that you can only have 8. 8's the highest number you can go to. So look at the Roman numeral 1, 2, 3, 4, 5, 6, 7, and this is column 8. Okay? That tells you how many electrons are in the valence shell. That's going to tell you that, you know what? The chemistry of carbon and silicon are very similar. Why? They both have 4 electrons in their highest energy level, in their valence shell. That sodium and potassium behave very similarly. That sodium and potassium behave more similarly than sodium and magnesium. Why? Because they both have 1 electron in their valence shell. And so again, from the periodic table, things are related to one another, left to right, because of adding 1 or subtracting 1 proton and electron. And up and down, because their valence shell, their outermost energy level, is similar, therefore they react in similar ways. They react in the same combinations with other, for example, metals and nonmetals. So they're going to react in the same combinations. Why? The combinations are based upon the number of electrons in the highest energy level in that valence shell. So just a little taste of where we're going. But this completes all but the last section of Module 3. There's a section here called The Amazing Design of Atoms. And frankly, it's a bunch of really cool pieces of information. There's not a lot of testable material in there, but it's some really cool biblical integration. It talks about how if there was a differences of less than 0.2% in the masses between the protons and neutrons and all these different kind of things, how life as we know it would cease to exist. So it gives a presentation about the uniqueness and the design and the intentionality behind chemistry, behind matter, behind everything that is. And it's a really interesting piece. So I'd encourage you to go through and read it. You know, ultimately what the author says is that the exactness of the design and the inability of our understanding of how anything other could work shows evidence that there is a creator. Shows that this is not just happenstance, but shows it's very intentional design. Remember yesterday, or the other day, when we were watching Crash Course, they talked about water, and we're not ready yet for that. It's a little beyond our ability. But they just made the statement, if it wasn't this way, then life as we know it would instantaneously cease to live. Everything would immediately die. Those kind of things. We're going to see that over and over in chemistry, that the balances or the percentages or the relationships are exactly where they need to be. And as best we can understand it, they can't be anywhere else, or life would not exist as we know it. So that completes Module 3. Hope you have the rest of the homework that's not in tomorrow. I'd like to start going over the homework tomorrow, and then Friday either finish the homework review or take your questions from EPPs that you don't understand on Friday as well to help you prepare for Monday's exam. All right?